After its billion-mile journey from Earth, the Voyager 1 spacecraft sent back pictures of man's closest look yet.
The most distant human-made object, NASA's Voyager 1 spacecraft.
We have ignition and we have liftoff.
Marking a major step in the study of interstellar space, NASA's Voyager 1 was launched to explore regions no Earth-made object has ever been. This silent probe, with a memory 3 million times smaller than a mobile phone, continues to serve as a remarkable agent in space, transmitting data that challenges our very comprehension of the cosmos. And now, after 46 years of exploration, finally, something impossible has emerged. This spacecraft made a discovery that changes everything about our knowledge of the universe. What exactly did Voyager 1 stumble upon in the dark heart of space? What does this mean for us? Join us as we explore the details. The historic journey of the Voyagers into interstellar space. Back on September 5th, 1977, Voyager 1's space exploration journey began, lifting off from Cape Canaveral, Florida, by the Titan IIIE Centaur rocket. Just 15 days later, on August 20th, 1977, Voyager 2 followed suit, setting out on a twin adventure into the cosmos. The primary mission of these spacecraft was to explore the gas giants of our solar system, namely Jupiter and Saturn, along with the moons in orbit around them. Little did they know, this dynamic duo would surpass their initial objectives, venturing into the farthest reaches of our celestial neighborhood. Today, Voyager 1 and 2 have earned their names in the record books. Outlasting any other spacecraft in history, these unrelenting explorers have traveled farther from Earth than any other human-made objects. They've even boldly gone where no one has gone before, into interstellar space, becoming the first human-created objects to achieve such. Their journey into interstellar space, breaking free from the sun's influence and flying into the uncharted realms of the galaxy, has been a treasure trove of invaluable data for scientists. These pioneering interstellar probes continue to terrify physicists with unexpected findings. One of these findings shows the unpredictability of the Voyager mission, the precision in design of Voyager. Before we delve into this shocking discovery that the Voyager probes encountered more than 12 billion miles from Earth, let's talk about the design of the Voyager spacecraft. Voyager 1 and Voyager 2 were meticulously designed stable platforms with a rotation rate more than 15 times slower than the hour hand of a clock. This design choice minimized visual blur as the spacecraft captured images and data hurtling through space. Their impressive imaging capabilities began to captivate scientists and the public well before their encounters with the outer planets. The Voyager also has 8-track tapes that are now considered outdated. However, they were immensely appreciated back then since digital storage wasn't a thing in the early days of space exploration. Scientists needed something reliable and tough to store all the precious scientific data about the outer planets, moons, and interstellar space. And that's just what the trusty 8-track tapes do, the indestructible workhorses of the cosmic age. What's on these tapes is the key to unlocking some of the universe's most profound mysteries. These old explorers have been through extreme temperatures, cosmic radiation, and the vast vacuum of space. Yet, they keep on trucking, and not only do they survive, but they thrive. One of the strategies employed to aid the traveling of the Voyagers is the gravity assist maneuvers, which eventually lead them to the impossible discovery they recently encountered. They needed a boost to reach distant destinations and snag some priceless data, something more than their engines could muster. And that's how we have gravity assists. Instead of relying solely on their own propulsion systems, these spacecraft engaged in a celestial dance with some heavyweight planets in our solar system. The genius behind this maneuver was conserving precious fuel and gaining the velocity needed for their grand tour. Gravity assist, also known as gravitational slingshot, is all about passing by a planet and snagging some of its momentum. Imagine Voyager 1 sidling up to Jupiter, a massive gas giant with a gravitational pull to match. With the precision of NASA's brightest minds, Voyager 1 swung by Jupiter at just the right angle and speed. Jupiter's gravitational tug accelerated the spacecraft, serving as a cosmic boost and giving it the oomph it needed. Note that if Voyager 1 had approached Jupiter at the wrong angle or speed, it could have been a cosmic catastrophe, sending the spacecraft off course. The precision needed is mind-boggling, but the cosmic ballet choreographers at NASA's Jet Propulsion Laboratory nailed it not once, but multiple times. While the Voyager missions leaned heavily on gravity assist maneuvers, another unsung hero that played a pivotal role is the Deep Space Network, DSN. The DSN is a network of colossal radio antennas strategically scattered across the globe. Ranging from 26 meters to a whopping 70 meters in diameter, these gargantuan dishes act like cosmic megaphones, enabling us to stay in touch with spacecraft beyond our planet. Now, let's get into its role in the Voyager missions. The Voyager probes, armed with cameras, sensors, and instruments, were essentially our eyes and ears in the vast cosmic expanse. To decipher the data they sent back and provide new instructions, we needed a robust communication system, and that's where the DSN stepped into the spotlight. As scientists send commands via the DSN, they also receive data in the form of signals that the DSN is quick to catch. It's a two-way conversation between Earth and the farthest human-made objects in the cosmos, the impossible discovery made by Voyager 1. We have acknowledged the genius work that goes into driving Voyager 1 and 2, so it's time to discuss a mind-boggling discovery made by these twin explorers in space. As the Voyager probes embarked on their interstellar journey, the heliopause was a significant checkpoint on their cosmic roadmap. This boundary marks the separation between our sun's sphere of influence and the vast interstellar expanse beyond. The precise location of the heliopause was a bit of a puzzle initially, with early estimates placing it as close as Jupiter. However, refined calculations, particularly those by astronomer Bill Gurney in 1993, projected the heliopause between 116 and 177 astronomical units, AU. To put things into perspective, 1 AU is about 93 million miles, the distance from Earth to the Sun. Gurney's projections turned out to be remarkably accurate, as Voyager 1 reached the heliopause about 2 decades after its launch at 120 AU from Earth, detecting the anticipated rise in plasma density that qualified the heliopause. However, scientists were presented with a problem. When Voyager 1 reached the heliopause, it observed an increase in plasma density but no significant shift in the ambient magnetic field direction. This was unexpected, as a transition from a region where the magnetic field originates from the Sun to one governed by other stars should have prompted a noticeable change. Voyager 2 added to the mystery, reaching the heliopause at the same distance as its twin, but also failing to detect any magnetic field changes. Theoretical models predicting the behavior of the heliosphere and its interaction with the interstellar environment faced challenges due to these unexpected observations. The heliosphere, expected to fluctuate in sync with the Sun's 11-year cycle, didn't align with the data gathered by the Voyagers. The solar wind, ebbing and flowing with the Sun's rotation, was strongest when Voyager 2 reached the heliopause. The predicted position of the heliopause should also have been further out than 120 AU, adding another layer of complexity. Nevertheless, the Voyager's data have proved invaluable for refining theoretical models. Scientists now believe that our Sun has transitioned from a hot, ionized zone to a partially ionized section of our galaxy. This transition was likely triggered by nearby supernovae, ancient stars that exploded, heating the surrounding area and removing electrons from nearby atoms. The boundary between these regions can be likened to a seaside with turbulent waves and mixed magnetic fields. While the degree of turbulence can vary, the Voyager's observations have unveiled small-scale changes near the heliopause, but negligible variations on larger scales. Other significant discoveries by the Voyagers that enlightened scientists. Beyond this discovered peculiarity of the heliopause, the Voyagers have made more discoveries that serve the scientific community. Months before Voyager 1 reached Jupiter in 1979, the spacecraft had started beaming back images, unveiling the gas giant's swirling clouds and the iconic Great Red Spot. However, it was the revelation of active volcanoes on Jupiter's moon, Io, that truly stole the spotlight. Slightly larger than Earth's moon, Io emerged as the most volcanically active body in the solar system. The spacecraft's instruments detected peculiar signals from Io, and the vivid images they captured showcased towering volcanic plumes and a surface scarred by the ejection of volcanic material. Pele, one of Io's most prominent volcanoes, erupted 30 times higher than Mount Everest, blanketing an area nearly the size of France. The Voyager's observations of this alien moon laid the groundwork for the groundbreaking discoveries that would follow in the years to come. Another standout revelation was the unearthing of Jupiter's rings. Though subtle, these rings added an extra layer of fascination to the already intriguing gas giant. And if that wasn't enough, Voyager 2 dropped the bombshell that Europa, one of Jupiter's 53 named moons, sports an icy shell over 60 miles thick. These findings didn't just defy expectations, they ignited a scientific frenzy, prompting further investigations into the potential habitability of icy moons. As the Voyagers bid farewell to Jupiter, they snagged a gravity assist, a parting gift that propelled them towards Saturn. Escaping the sun's gravitational clutches would have been a no-go without this crucial boost. With the cosmic kickstart, Voyager 1 and Voyager 2 embarked on separate odysseys, each heading towards uncharted territories. Voyager 1 took a scenic route, passing close to Saturn's moon Titan, enveloped in an orange, hazy atmosphere that stirred scientists' curiosity, leading to in-depth studies of its complex chemistry. Then, veering northward and departing from the planetary plane, Voyager 1 ventured beyond the bounds of our solar system. On the flip side, Voyager 2 went on a planetary tour, hitting the outermost planets. In 1986, Voyager 2 pulled off a historic flyby of Uranus, unearthing 10 previously unknown moons and increasing the planet's moon count. 3 years later, it reached Neptune, unraveling the unique features of this distant ice giant. Its discovered wind speeds of up to 1,000 miles per hour on Neptune set a record for the fastest winds in our solar system. Voyager 2's close encounter within 2,980 miles of Neptune's azure methane-rich atmosphere offered these unprecedented insights. Triton, Neptune's largest moon, also turned out to be a deep freeze, registering surface temperatures plunging to minus 391 degrees Fahrenheit or minus 235 degrees Celsius. It had ice volcanoes spewing nitrogen gas and icy particles 5 miles into its thin atmosphere. These revelations broadened our comprehension of the diverse and intricate celestial bodies, even in the farthest corners of our solar system. Finally, here is the most iconic image captured by Voyager 1. As the spacecraft continue their remarkable voyage, NASA has implemented measures to prolong their operational lifespans. It did this by switching off non-essential components of the spacecraft, like the camera and heaters, just to conserve energy. This would ensure they can operate well into the end of the decade, with an estimated mission end date of 2030. However, part of the Voyager mission's imaging team, Carl Sagan, passionately argued for one last set of images before shutting down the cameras on both spacecraft. These images, he believed, would be humanity's parting gift, a final glimpse of our home planet from the cosmic depths. Sagan's persistence eventually paid off, and on Valentine's Day in 1990, Voyager 1 turned its lens toward the inner solar system, capturing the iconic pale blue dot. Taken from a staggering distance of 3.8 billion miles, this image remains the farthest snapshot of our planet. In it, Earth appears as a minuscule pale blue speck, barely distinguishable in the vastness of space. The realization hit like a cannonball that we all are so small in the grand scale of the universe. The Voyager mission continues to unfold like a space-age superhero comic, an astonishing tale of durability and longevity. Even after 40 years, they're still out there, beaming back valuable data from the cosmic fringes of our celestial neighborhood. These genius human creations may eventually thrive beyond 2030 and witness millions of years after the extinction of the human species. Let's hear from you in the comment section below. Also, make sure to like this video if you enjoyed it and subscribe to the channel for more. See you in the next one.